Hi, so thanks for coming everyone and for inviting me to this summit. I'm Wook Song. I'm a PhD candidate at the Software Platform Lab in Seoul National University located in South Korea. And today I'm going to talk about running Apache Beam programs on our project Apache Nemo, which is currently an Apache incubator project, mainly being developed by our research group in Seoul National University. All right, so since Apache Nemo might be a bit unfamiliar with you, let's first get a little overview before we get started. So we know how data processing works. First, there's a data processing application coded with frameworks like Beam or Spark. Then there's a bunch of different data processing frameworks with different designs, and there's a pool of computing resources that we can use to run these applications. The thing is that such resource environments are not just uniform and ordinary, but there's a lot of different types of resource environments where such difference becomes problems in the existing data processing frameworks. For example, one can try using cheap transient resources that are collected from the idle resources in data centers, which can be evicted at any time. Or one could run their applications on data centers where computing and storage resources are managed separately. Otherwise, one could try running their application in data centers that's distant from each other, connected with heterogeneous network bandwidths, or they could be facing a skewed data set where a specific key is overly popular. And the list can go on and on. In order to solve the different problems, until now, one needed to intensively modify the internals of the data processing frameworks to adapt them for each of the different and specific environments. But Apache Nemo tries to do this without such efforts and tries to support the multiple different environments on its own. So in order to do this, Nemo tries to schedule the workloads and to transfer the intermediate data efficiently by optimizing the related properties of big data applications by tagging each of the P transforms and the P collections with the optimal properties. It bases itself on 4 aspects. It's designed in the way so that such optimizations can be easily extended to new environments with new properties, only needing to implement just the new components, just the new modules, and without having to reinvent the wheel. Next, it aims to flexibly optimize the applications in units of P transforms and P collections instead of optimizing the whole workload, entire workload. Also, it's designed so that the different optimizations can be composed together, so that one could use multiple optimizations simultaneously while ensuring for correctness, so that the workload is actually executed in the designated way. So this is the basic architecture. With the principles, Nemo first takes the data processing applications, primarily Apache Beam applications, as well as primitive Spark RDD programs, and turns them into our intermediate representation graph, which I'll often refer as a IR from now on. And on the IR, it applies a specific set of optimizations, hand-tuned optimization passes designed for each of the different use cases to tag each IR vertices, P transforms, and edges, P collections, with specific properties that run efficiently in the specific use cases, which could be understood and executed later by a Nemo-compatible runtime. So if you're running one or more data centers or clusters and want to use your computing resources more efficiently, or if you want to run your data processing applications faster under your specific resource configuration, environment or condition, Nemo would be a very nice candidate as your Beam runner or your data processing framework. So we'll now demonstrate this with some real examples. So how a Beam application basically is translated into a Nemo IR, directed acyclic graph, DAG, is simple. P transforms are wrapped and translated into IR vertices, and P collections are translated into IR edges. Let's use a real code example to illustrate this better. On the left, you can see a simple Beam program code performing a text read followed by map elements, group by key, and another map elements, as you would see in a simple map reduce workload. Here you can see that each of the P transforms are translated. P transforms are translated into an IR vertex, which each wraps a P transform into the IR vertex abstraction, which are connected by edges describing the dependency of the operations. Basically, you can think of an IR vertex as a wrapper for the P transform so that we can perform specific Nemo optimizations on top of the P transforms and P collections. In our example, let's observe a case that can occur on the shuffle edge before the group by key operation that requires collection of data from multiple machines for data containing the specific keys. So we're going to observe a case where it's a large-scale shuffle where we need disk instead of because the data cannot fit in memory. So during a large-scale shuffle operation, when retrieving data on multiple machines, each designated with the keys of the data to retrieve from the previous operations, it incurs random disk reads and read overheads from multiple disks up there, as disk usage is inevitable because the data does not fit in memory. So, and this happens in not only one, but each of the group by key tasks. So the overhead results in a huge bottleneck overall in the data shuffling operation, and it's a very important problem while performing large data analytic jobs. To solve this issue, researchers have proposed methods for batching the disk reads to prevent the random disk reads, to change them to a more sequential disk read operations. So such solution can be expressed as follows on the slide, shown on the slide. The solution pushes the data with the specific keys to a specific relay vertex in memory that writes the data to disk sequentially in the way that it would be read by each of the following group by key tasks. So how Nemo performed this optimization is simple and can be done in just a few lines of code. This is just a pseudocode, by the way, and the actual implementation is in Java. It first seeks for the shuffle edge and creates a new relay vertex and inserts it in between the shuffle edge. After that, it tags the incoming and the outgoing edges of the relay vertex with the appropriate execution properties that distinguish how the intermediate data should be transferred from and to the relay vertex. In our case, it's the push memory and pull disk properties. It means you want to push the data to the relay vertex and in memory, and you want to pull the data from the relay vertex through the disk. So with the optimized IR DAG, the Nemo master distributes and schedules the DAG to Nemo executors, multiple executors, so that each tasks carry out their work designated earlier by the Beam P transforms. As shown on the slides, the read and map tasks run in a pipeline manner in a single executor and pushes their outputs to the following relay vertex which writes the intermediate data on its disk. And then afterwards, then the data written on the disk can be pulled and read sequentially by the following group by key and map tasks. So our evaluations show that for Spark, you can see that the reduced tasks take up most of the job completion time for large data sets. And whereas Nemo successfully keeps the ratio small, although it results in a slight increase in the proportion of the map tasks in the job completion time due to the relaying out operations. Here's another evaluation. This illustrates the same results where Nemo keeps high disk speed throughout the entire workload. It's shown in yellow and green, and resulting in short job completion time, whereas Spark results in a very small disk throughput while performing long, reduced tasks, taking up most of the JCTs. So yeah, that was example one, and I brought another example. A second example is to demonstrate Nemo, how it uses transient resources, cheap transient resources. So basically, transient resources for those who do not know about it, they're simply resources that are left over and left idle in data centers as latency critical jobs usually over-provision resources for peak traffics. Obviously, such resources are cheaper because they're left over, but has to give up the resources once the original jobs request to return their resources. So what happens when running tasks on such resources is that container evictions can result in abrupt, frequent, and indeterministic task terminations, which also results in loss of intermediate data. So in order to solve this, researchers have distinguished the workload into ones that depend on a large number of parent tasks as valuable tasks, as you can see on the right, and the ones with less dependency as less valuable tasks. So, for example, if we look at a simple MapReduce application, the map tasks have no dependency with the parent tasks. It doesn't have any parent tasks. So it's considered less valuable, and we place them on transient containers. Whereas each of the reduced tasks are depend on multiple map tasks because there's a shuffle operation going on there. So they're considered more valuable, and we place them on reserved containers. So to compare the cases, general engines place tasks without distinguishing the different containers, while our optimization places tasks according to their valuability. So now, if an eviction occurs in transient containers while performing data shuffle, data is lost on the general engines, while our optimization safely keeps the data on reserved containers. So consequently, it results in cascading recomputations of multiple tasks in general engines, and whereas it doesn't invoke as much recomputations when the optimization is applied. So this optimization can also be implemented with simple code as well. Just a few lines. It looks at each vertex topologically and tags them accordingly with transient and reserved containers. So the ones with the less valuable dependency are tagged with transient containers, and the ones with more valuable dependency, like shuffle or many-to-one, or those that can be pipelined from those vertices are tagged with reserved containers. You can also notice that the data is pushed away from transient containers as soon as possible to reserved containers so that the data is evacuated as soon as possible. Now, comparing Spark with Nemo and Pado, which is the work that originally suggested the idea, Spark suffers from all rates of evictions. For 40 minutes and 20 minutes, it goes above the line. And whereas Nemo and Pado remains rather indifferent and stable for each of the different eviction rates. So this is the x-axis is the mean time to eviction on transient resources. So now, with all these passes, for example, one wants to apply the transient container optimization on top of the large shuffle optimization that we have seen earlier. Let's suppose that we have a DAG ready, optimized by the large shuffle pass. One simply needs to execute the transient resource pass on top of the optimized DAG as each optimization runs on its specified rules. So this is the resulting DAG if you apply both optimizations. So any Beam application can be optimized on our system in such ways, and I think it's very simple and intuitive. So in order to show this in action, I prepared a very short, compact video showing several demos for running different types of Beam applications on Nemo. It's very compact due to time constraints, so please pay close attention. So, yeah. So our first demo runs the good old batch processing application. It performs an analysis on a network trace log. The right side is what you would see if you run Nemo on your machine. And on the left, you can see the progress on the execution using our visualizer. It supports WebSockets, and you can see the status of the job as well as each of the tasks. Right. So the second demo shows a machine learning workload, multinomial logistic regression, running on Nemo. You can see the loss for each iteration on the output section on the right. It's going to come up in a second. Yep. There we go. And you can also visualize such iterative workloads, machine learning workloads, on the visualizer as well, with the support for visualizing large, long DAGs with lots of dependencies. Right, there we go. Yep. And third is a stream processing workload, the sixth query of the nextmark benchmark. And you can see the execution in action with the inputs and the outputs for the workload, for the queries being created and processed on the right. And this time on the visualizer, let's turn it on. On the visualizer, you can see that the DAG is actually not turned green because streaming workloads are expected to run continuously. Yeah. So lastly, we'll compare the performance of a large shuffle application on Nemo and on Spark. Here's the IR DAG, optimized with our large shuffle optimization paths. And we have launched both jobs at the same time to run the 3 terabytes TPCH benchmark query number 12. So for the time being, we fast forwarded by 145 times. You can see the progress bar going up very fast on Nemo, whereas on Spark, the progress bar is going up relatively slowly. So we had 36 minutes as the JCT on Nemo, whereas on Spark, it took more than 2.5 hours. So that was a short demo. And for the further details of our work, they'll be presented at the Usenix ATC 2019 conference that's happening next month in July in Renton, Washington, in the States, next to Seattle. So I'll be there as well, so feel free to say hi to me if you happen to pass by. Yeah. So before I finish, I would like to quickly mention a few ongoing works on top of Nemo. First is, of course, I think some of you have already guessed, but it's to apply machine learning on the optimizations. To solve the resource constraints problem that I described earlier, regarding the different resource environments, we providing the specifications of the resources that is available for a certain workload. And our idea is to use machine learning to place the different operators vertices to specific resources that can execute the work most efficiently. For example, like if a P-transform needs a lot of GPU power, we can place it on GPU nodes and so on. Right, so we store the metric data along with the information of our IR DAG on the database and use that information to generate and form decision trees like this, for example, using tree boosting or other tree generation techniques. As you can see, these decision trees lead to different JCTs and job completion time outcomes, and such results can be reflected on an IR DAG to produce smaller job completion time. This is an ongoing work in its early stages. So case 2, we also propose a method for using serverless frameworks for scaling out Bursty workloads. So this is a situation when streaming workloads suddenly require more resources due to input rate fluctuations or windowed operations. Nemo tries to invoke the serverless frameworks instead of virtual machines through existing serverless frameworks. As serverless frameworks provide faster resource provisioning compared to virtual machines and faster boot up time and can be invoked on demand. So with the serverless containers, we can migrate and offload the burden of the operations causing the bursts to the serverless framework containers to scale out without damaging the latency. This is also work in its early stages. Right, so our project is very young and it's in its early stages. I believe that it's promising though, and it has been an incubator project since the spring of last year. So with about 20 contributors, 220 pull requests, and 559 commits. We're working hard to grow the community. For example, like we're also participating in the Google Summer of Code program for 2 consecutive years to attract open source contributors. We have successfully mentored a single project last year. You've already seen the web user interface through the demo, and we are mentoring two projects this year. All right, so to wrap up, the Nemo Runner is already available, and the instructions are shown on the Beam website. Although you might need to run Beam applications through the run script provided by Nemo to actually fully utilize all of the options that it provides, you can still run your Beam application straight on Nemo just by specifying it as your runner. And I hope you could use it to run your applications with the optimizations that we provide. And we're looking for new contributors to be able to enrich the possibilities of Beam with our framework. So that's the end of the talk for today. And for those who think our work is interesting and want to participate, please refer to the links shown on the slides. And we're open to new contributors and new users. Thank you very much for listening, and I'll take your questions.
Thank you so much, Wook. Thank you. Unfortunately, we don't have the time to take on questions right now. So if you have any questions for Wook, I would encourage you to approach him during the coffee breaks and the networking opportunities that we'll have throughout the summit. So thank you.